Poly-harmonic principles of BNF central wavelength monitoring. In this section, we propose a microwave photonic method for monitoring CD in synchronization channel based on analysis of the BNF reflectance spectrum position. As the prototype of the CD measurement system, the methods described in were taken. A monitoring subchannel based on the analysis of the optical carrier signal reflected from the BNF was included in the method operation sequence. Before reflection, carrier of synchronization channel of QKD-CMC system is modulated by amplitude at the FCL/100 frequency in the data generation stage, where FCL is the frequency of the clock synchronization signal, 1 to 10 GHz. The presence of modulated components allows probing the position of the BNF, tuned by the sender to the optical carrier, and produces a mismatch signal for its detuning, in analogy with the microwave photonic method of FBG interrogation, presented by us in the given paper. Symmetrical 2-frequency probing signal was used. We additionally consider the methods of amplitude unbalanced 3-frequency and symmetrical 4-frequency probing. In the possibility of OSNR increasing till 10 to 12 decibels, when signal processing realized on frequency modulated component speeding envelope, was shown also for full telecommunication channel. We shall reanalyze these results from the point of our task view. We define the parameters, which could be used for registration in monitoring system, and carried information about interaction between double, 3, and 4-frequency probing oscillations and BNF. Symmetric double frequency probing radiation is a complex signal with amplitude and phase modulation. The main feature of this signal is that all of its components, instantaneous envelope at, phase theta t, and frequency omega t, depend on its component amplitude ratio A1, A2. We evaluated the modulation rate of double frequency signal. There too we will use the modulation coefficient, where Mx is sum of A1 and A2, and Amin is its difference. Calculation results for M delta, where delta is reference BNF detuning, are shown in for different, A1/A2. Dependence M delta, for differential 1/A2. We also define the phase gradient of double frequency signal under a component's amplitude changing. Calculation results of theta, delta, are shown in for different, A1/A2. Phase shift dependence theta, delta, on component amplitude ratio A1/A2. Analysis of the dependences M delta, and theta, delta, allows determination of BNF central wavelength shift, according to delta, during the measurement of modulation index manned phase theta of probing signal components A1 and A2 beating envelope. Produced on amplitude modulation coefficient or phase changing mismatched signals used to make correction in CD monitoring process or retuning the center wavelength of BNF. It is known from a number of works that 2-frequency probing, as simplest, does not always allow one to unambiguously determine the direction and magnitude of the BNF central wavelength shift from the wavelength of the carrier. Let us set the task of determining the position of the BNF central wavelength based on a 3-frequency amplitude unbalanced probing, relying only on the data coming from the photodetector PD to the ADC. Without changing the position of the carrier frequency of the probing radiation, we will shift the BNF in the range. For each position of the BNF, we analyze the parameters of the low-frequency signal at the output of the photodetector, tuned to determine the amplitude of the oscillations at the direct current, DC, the probing frequency FCL/100, and the doubled frequency 2 FCL/100. The characteristics of the reflected signal level calculated from the 3-frequency probing procedure on DC, 100 and 200 MGZ for the central frequency position and detuning, are shown in components reflected from BNF and their levels calculated for the 3-frequency probing radiation at central, carrier, position and its detuning. Taking into account the position of the BNF relative to the carrier, we can say analogically that we reduce the error in the CD measurement by 10%, 3 decibels. 2 pairs of probing signals shifted from the carrier are sent to the mediums of the left and right slopes of BNF. Bragg wavelength of BNF is equal to the carrier wavelength, different frequency inside pair is equal to 100 MHz. The outputs of photodetector signals are formed, corresponding to the beating of the first, channel 1, and second, channel 2, signal pairs. By measuring the difference between amplitudes of each beating envelope, one can unambiguously determine detuning sign and value of central BNF wavelength. 3 cases of DNF deviation are shown in 3 cases of BNF deviation for 4-frequency method. In the first point, the BNF offset from the resonance wavelength is absent, and the output amplitudes of beating envelopes are equal. In the second point, there is a slight BNF deviation, and the direction and magnitude of the deviation are determined by greater amplitude of beating envelopes. In the third point, there is a significant deviation, and the direction and magnitude of the deviation are determined by the presence of a signal of beating envelopes and its level in one of the channels.